Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review what was covered in week 3. So week 3 was all about integration with logs and logarithmic modeling. Now last week we did differentiation with logs. We figured out when we differentiate the natural log of some function of x, we just move that function to the bottom of the fraction and write its derivative on top. So that's exactly the same as saying if I integrate a function that looks like this, where I have a function on the bottom, its derivative on the top, it's just the natural log of what is on the bottom. So when we're doing indefinite integrals, make sure we add the c. So for example, the integral of 1 over x is just the natural log of x, and we need to add the c. Now, technically, it is natural log of the absolute value of x because, you know, when you take natural log, this can't be negative, but don't worry too much because we haven't covered absolute values. So what about something that looks like this? Well, it's not quite in the form of function on the bottom, derivative on top, because I would want a 4 on top. But note, I can write it like this. 3/4 times the integral of 4 over 4x. So why would I do that? Well, 3 over 4 times 4 equals 3. Now I've written it, so I have function on the bottom, but its derivative on top. So when I go and integrate this, I'm going to leave the 3/4 alone, and this will just be the same as ln natural log of 4x. And then I write the plus c and I'm done. So we're going to do something similar here. So we have 3x minus 2 on the bottom, but 10 on the top. The derivative of 3x minus 2 is 3. I really want a 3 on the top. I really want it to look like this. But I can easily make it look like this. So these two are the same things. I need to ask myself, what do I times by 3 to get to 10? Well, of course, that's just 10 over 3. Now these two are the same thing, but this is in the right form. So when I integrate it, it's just going to be 10 over 3 natural log of the function on the bottom, and I'm going to add the c because it's an indefinite integral. So how would we do something that looks like this? Well, what we're going to do is we're going to divide everything on top by x cubed. Of course, this means divide. So make sure you always write the dx. So we go x cubed divided by x cubed. Well, that's just 1. X squared divided by x cubed is going to be 1 on x. 4x over x cubed is 4 over x squared, and then we have minus 1 on x cubed. So what we're going to do is integrate each of these terms one by one. So you remember to integrate 1, we just get x. The integral of 1 on x is just the natural log of x. Okay, so don't worry about the absolute value, like I said before. So how do we integrate these? Well, these are actually the same things you were integrating last semester. This is 4x to the minus 2. So remember what we do is we increase the power by 1 and divide by the new power. So it will be minus 4x to the minus 1 or minus 4 on x. So same here, this is x to the minus 3. We increase the power by 1, so we get x to the minus 2, and divide by that new power. And then, of course, we have to write our plus c at the end, easy as. All right, let's move on to a harder question now. So when you have a situation like this, polynomial on top, polynomial on the bottom, the polynomial on top has higher degree, use polynomial long division. So we're saying how many times does x minus 2 go into x cubed minus 4x squared plus x plus 1. So we go x into x cubed goes x squared times. When we get a term up here, we multiply it by this to calculate the remainder. So x squared times x squared times minus 2. So to calculate the remainder, we subtract. Negative 4x squared, subtract negative 2x squared, gives me negative 2x squared. So we divide the remainder by the leading term, we get minus 2x. Bring this one down. So as I said, anytime you get something up here, times by what's here. So minus 2x times x is minus 2x squared. Minus 2x times negative 2 is positive 4x. Calculate the remainder by subtracting. Whenever we get a remainder, we divide by the leading term. So minus 3x divided by x is minus 3. So bringing this one down, and now we go minus 3 times x, and then minus 3 times positive 2. So when we subtract and get the remainder, we get minus 5. So what does that mean? It means that this polynomial divided by this is equal to x squared minus 2x minus 3, but then we've got a remainder of 5. So it's minus 5 over x minus 2. So this is just the same as when you do division with numbers. You know, 37 divide 3, well, 3 goes into 37 12 times remainder 1, and we write over 3. What we're dividing by goes on the bottom, and the same here. The remainder was minus 5, so it's minus 5 over what we were dividing by. So we've done all the hard work. This is actually really easy to integrate. We just go term by term. Integral of x squared, increase the power by 1, divide by the new power. We do likewise for 2x and negative 3. So now we know how to integrate this, because of course this is just the same as minus 5 times 1 over x minus 2. Well, the derivative of 1 over x minus 2, we've got a function on the bottom, its derivative on top, that's just ln of x minus 2. So there we are, done that. We'll move on now to logarithmic modeling. So logs are used to model so many things in the real world. For this example, we're going to look at the Richter scale, which is about measuring the magnitude of an earthquake. So here m is magnitude, x is the intensity. So the way they measure intensity is the movement of a seismograph. I think it's 100 kilometers from the center of the earthquake or something like that. And we have this 0.001 here. That's the normal movement of the earth. This is like a comparative scale. When you're measuring the magnitude of the earthquake, you're measuring how much the seismograph has moved compared to what it normally moves as its default. So this Richter scale is what we call a logarithmic graph. It turns out for each one increase in magnitude, then the intensity is multiplied by 10. So for example, if you had a magnitude of 2 earthquake versus an earthquake with magnitude of 3, the one with magnitude of 3 would be 10 times more intense, 10 times more movement of the seismograph. So we're going to look at that in this example here. Earthquake felt in 2 cities, Canberra 5.4 on the Richter scale, Sydney 7.2. How many times more intense was the earthquake felt in Sydney? We're asking how many times more would the seismograph move in Sydney than it would in Canberra. So what we can do is make this a little easier to work with. You know from our log laws that when you subtract logs, you just divide their powers. We're just going to write this as log base 10 of x, where x is the intensity, over 0.001. So what we're going to look at is the difference in magnitude in Sydney, that's what ms means, and mc the magnitude in Canberra. Well, we know the difference is 1.8. So it's just 7.2 minus 5.4. So using this formula up here, I'm going to call the magnitude in Sydney, it's going to be log base 10. I'm going to call xs the intensity in Sydney, and then I'm going to subtract the magnitude in Canberra. So I'm going to call xc the intensity in Canberra. So now I'm going to use the log laws again to combine this into one log. So I just go this divided by this. But when you're dividing like this, I can cross out those two numbers there. I'm just left with xs over xc. So if I want to get rid of the log, the way you undo log base 10 is raising 10 to the power. So what I have is 10 to the power of 1.8. And getting rid of the logs, I'm just left with xs over xc. So what that means is the ratio of the intensity here is 10 to the power of 1.8. So 10 to the power of 1.8 approximately equals 63.1, and that means the intensity in Sydney was about 63.1 times what it was in Canberra. All right, let's now move on to productivity models. So productivity models are generally used to model things like humans gaining skills. So for example, if you go to the gym, you know you make a lot of progress early, but the amount of progress you make decreases over time. You might increase your bench press by 10 kilos in 2 weeks, but you won't continue at that rate forever. Another example is like learning language. Turns out when you're really young, you learn heaps and heaps of new words each year, but the number of new words you learn each year goes down as you get older. It turns out kids are just better at learning languages. So this curve looks like a log graph, and that's why the equation for a productivity model has a log function. So we use the natural log for this because it's easy to differentiate. Now in this, P is like whatever units you're gaining, and T is time. It could be days, weeks, years, whatever. So note we have to have T plus 1 because you can't take the natural log of 0. So this allows us to input T equals 0 by having the T plus 1 there. So let's look at an example. Athlete wants to bulk up and gain weight. After 4 weeks, he's gained 3 kilos. After 8 weeks, he's gained 5 kilos. And we're going to find the rate at which he's gaining weight after 8 weeks. So first, we need to find an equation of this form and find what AB is. So in this example, T, which is always the time, is going to be weeks, and P is going to be the weight gain in kilograms. So it turns out after 4 weeks, we have he's gained 3 kilos. So what that means is A plus B ln, I'm going to substitute in T for 4, so we get ln 5 is going to equal 3 kilos. So we know that after 8 weeks, he's gained 5 kilos. So that means A plus B, I'm going to substitute now T for 8 into this formula. So A plus B ln 9 is equal to 5. Now, we have simultaneous equations here. I can simply subtract to get rid of the A's. So I go A minus A. B ln 5 minus B ln 9 gives me this, and 3 subtract 5 is negative 2. So B is just going to be negative 2 divided by this. So after I found B here, I'm going to substitute into either one of these equations to find A. That's really easy to do. If I substitute it here, A is just going to be 3 minus 3.4026 times ln 5. So A is approximately minus 2.4763. So now I have my equation. I'm going to get rid of this, so please pause and copy down if you need it. So I just found that my equation PT equals A, which we figured out was this, plus B, which was 3.4026, times ln of T plus 1. So the question asks for the rate at which he's gaining weight after 8 weeks. So the rate of change is the derivative. I need to differentiate this function. It might look complicated, but it's really easy. When we're adding or subtracting constants, when we differentiate, they vanish. So this is just going to go away. Now we're just going to differentiate this. Well, the derivative of natural log of T plus 1 is just 1 over T plus 1. And we're timesing by this coefficient here, so that's just going to go on top, 3.4026. That's why we use natural logs here rather than log of another base, because it's easy to differentiate. So of course, after 8 weeks, all I need to do is take this derivative and substitute T for 8. So putting that in my calculator, I get about 0.378. So remember, P was in kilograms, T was in weeks, so he's gaining about 0.38 kilograms per week. All right, thank you so much for tuning in, and sorry for the long video. This has been the luckiest maths teacher in the world. Have a great day.